Howdy everyone. Well, I wanted to re-record the audio for this portion of the lecture so that you don't have to listen to a slow motion version of Jabba the Hutt for the last 5 minutes of the lecture. So essentially what I was saying here is that you have the situation where lambda is decreasing as the unburned gas pressure increases, but the laminar flame speed also decreases as the unburned gas pressure increases. And so again, when we look at the burnup time, this tau b, lambda divided by S sub L, there ends up being really no effect, no noticeable effect of the unburned gas pressure on the burnup time. And so if we take a look at what the net effect is then on the burnup rate, the dmB by dt, we basically show that the burnup time for the high unburned pressure case is about the same as the burnup time for the low unburned pressure case. So really the only thing that's being affected by the increased pressure, say as a result of boosting, is that we would have a longer flame initiation period. So if we look at our mass fraction burn curve, what you would have seen just there on the video is I was basically just drawing over what I had already drawn before for the mass fraction burn case. And then I also noted that the spark timing that we identified before as the, which is true, the maximum brake torque spark timing, but we could say that it was the spark timing of maximum brake torque for the low unburned pressure case. And then because the high pressure case requires a longer flame initiation period, we have to advance the spark timing in order to maintain maximum brake torque timing. In other words, because the burn rate is the same for the high pressure case as it is for the low pressure case, that rapid burning period, the delta theta B, is the same between high pressure and low pressure cases. That portion between 10% and 90% is going to look the same between those two situations. And so because the flame initiation period is longer, I consequently have to have an earlier spark timing with my high pressure case, because the higher unburned gas pressure leads to a lower laminar flame speed, causing there to be a longer flame initiation period, causing there to be a need to advance the spark timing for the high unburned gas pressure case. Okay, so then what we did is we went back to the notes and we started looking at a influence of the various parameters that can affect the mass fraction burn curve. And so the first parameter that we looked at was the fuel air equivalence ratio, phi, and I'm highlighting here the mass fraction burn curve for the leanest case, which is 0.6, an equivalence ratio of 0.6. And then I point out the fact that the near stoichiometric mass fraction burn cases, that associated with 0.9 and that associated with 1.10, basically have the steepest burning curve. Okay, if you compare the slopes of the 0.9 and 1.1 case to the 0.6 case, you notice that there's a much steeper burn rate for that slightly rich case. I also highlighted the fact that there's not a stoichiometric ratio, and what we would see is that the stoichiometric ratio is even still not as fast as that equivalence ratio of 1.10. That really ends up being the fastest burn rate that we have. Okay, so what I was highlighting on this slide, and what I encourage you to do, is to essentially use what you know or what you learned about laminar flame speed and the flame initiation period, and what you learned about the entrainment rate, dme by dt, and the burnup rate, dmB by dt, to predict what would happen to the flame initiation period and the rapid burning period based on your analysis of these various parameters, right? In other words, what happens to laminar flame speed as you change fuel air equivalence ratio? what happens to the entrainment rate as you change fuel air equivalence ratio, what ultimately happens to the mass burn rate, the dmB by dt, as you change fuel air equivalence ratio. I then highlight that this next slide is basically the same data that you see on slide 18. It's just we've changed the x-axis scale. Rather than go between 330 and 480, we go between 340 and 410, and that gives us a zoomed up picture of what's going on with the mass fraction burn as we change fuel air equivalence ratio. I then highlight slide 20, which is showing the mass fraction burn curve as a result of different EGR levels, looking at 0%, 10%, 20%, and 30% at fixed air fuel ratio and fixed spark timing. And again, I encourage you to use what you know about laminar flame speed and the mass entrainment rate model and the mass burnup model to predict how EGR ultimately affects the mass fraction burn curve, and see if you can show the same type of analysis. And then finally, the last curve is showing you the mass fraction burn as for various spark timings, looking at spark timings of 300 crank angle degrees, which would be 60 degrees before top dead center, and all the way to spark timings closer to top dead center. And again, I made the encouragement that you go through your laminar flame speed analysis, your entrainment rate analysis, and your burnup rate analysis, and see if you can predict what happens to the mass fraction burn curve as you change your spark timings. Okay, so at that point, slide 22 is basically as far as we get in the semester, and so I essentially at this point just thank you for all of your hard work that you put into the semester. This is certainly a very busy class. 410, 611 there's a lot of work associated with it. We learn a lot about many different things related to internal combustion engines and its reliance, of course, on thermodynamics and combustion, and trying to pull it all together with an actual practical operating device, which we call the internal combustion engine. So I thank you for all of your hard work, and I wish each of you well, and good luck on exam 2 and lab number 4. And certainly, please feel welcome to email me with any questions that you might have in preparation for exam 2 or lab 4. And of course, feel welcome to reach out to me with any questions you might have in the future related to engines, thermodynamics, or anything else you might want to talk about. Thanks very much. Have a great day. Good luck with your exams, and stay in touch. Thank you.